In the laboratory, we need a relationship between the microscopic properties, numbers of particles, and the macroscopic properties, the mass that we can measure. And we find that using relative masses. We take carbon-12 as the standard and take all other masses relative to that. So 12 grams of carbon-12 has Avogadro's number 6.02 times 10 to the 23rd particles of carbon-12. Hydrogen is 1/12 as massive. So 1 gram of hydrogen has 6.02 times 10 to the 23rd particles, a 12-to-1 ratio. And I've listed on this table a few other atoms and molecules and their relative masses. Here's oxygen, for example. It has 16 times the mass of hydrogen. So if I wanted to react oxygen and hydrogen atoms in a 1-to-1 ratio, I should keep the mass ratio 16-to-1. What if I wanted to react them in a 2-to-1 ratio, 2 hydrogens for every oxygen to form, say, water? Well, then I'd have to have 2 grams of hydrogen for every 16 grams of oxygen, a 2-to-1 relative mass ratio. I can do this with the molecules themselves. In fact, I can add up the atomic relative masses to get the molecular relative masses. Simplest case, hydrogen, H2, there's 2 hydrogen atoms, so it has twice the relative mass of hydrogen atoms, or 2. Oxygen, 32 oxygen molecules, twice as massive as oxygen atoms. Here's a couple molecules, H2O and CO2, water and carbon dioxide. Water, relative mass 18, that's 1 oxygen, 16, and 2 hydrogens, 1 each, that's 18. And carbon dioxide, the sum of carbon and 2 oxygens, 44 grams per mole. Now when you look at water and carbon dioxide, I've written water, a 3-atom molecule, as bent here, and carbon dioxide, also a 3-atom molecule, as linear. So how do I know one is bent and one is linear? Both 3-atom molecules. Well, that's the nature of the quantum mechanical interaction of the electrons that form the bonds in these molecules. And we'll study that in detail in this course. I've got a couple other elements here. In fact, we can think about how much is in a mole and look at this table more carefully. So a mole of water, let's say, that's 18 grams, 6.02 times 10 to the 23rd particles, 18 grams, that's say about this much water in the solid or the liquid phase. If it were in the gas phase, the volume would be about 1,000 times as large. But here's 18 grams of water. That's not very much, 1 mole. So let's look at 55 mole samples of some elements and molecules. Here's water. Now, water 55 moles is 55 times 18 grams of water. But the cool thing is, here's 55 times 18 grams of water, but I know how many particles are there. There's 55 times Avogadro's number, 55 times 6.02 times 10 to the 23rd particles in here. Now, I also have carbon. Here's 55 moles of carbon, and this has the same number of particles as water particles. They're both 55 moles. And their masses, actually, they're quite similar. And we can look at the table and see that water has relative mass 18, carbon relative mass 12, so those are very similar masses. Now, I also have aluminum here. Now, aluminum has mass about, well, looks like twice carbon. And yeah, I feel that. This is twice as massive, 55 moles of aluminum, about twice as massive as 55 moles of carbon. I also have lead. I can barely lift the 55 moles of lead. Here's 55 moles of lead, very massive, because each lead atom is something like 8 times the mass of the aluminum atoms. So very much more massive, 55 moles of lead than 55 moles of aluminum. Both the same number of particles, but each lead particle is something like 8 times heavier. So that's a lot of mass. Now, you may be curious, Why are these numbers for my relative masses not exactly integers? Well, that's because in nature, every carbon, for instance, does not have a mass of 12. There's some carbon atoms out there that have a mass of 13. In fact, about 1% of all carbon atoms in nature have a mass of 13. So when you look at naturally occurring carbon, you get an average of the carbon 12s and the carbon 13s to give this average molar mass of naturally occurring carbon. Same thing with aluminum and phosphorus and iron and lead. They have naturally occurring heavier and lighter versions. We call them isotopes. So this is an average over all the isotopes of the various elements that have different masses. Once we have a table of all relative masses, we can calculate relative masses of atoms and compounds and use them to determine the masses we need to perform our chemical reactions.